Well, a warm welcome, everyone. Thank you for joining here. Get yourself ready with a notebook. Grab a pencil or a pen. Whatever you choose to write with is fine. This is math from the void. Math coming at you out of nowhere. And today we have some Calc BC standards practice. So this is going to be the Calc BC FRQ standards practice series. And we're just going to simulate some questions that would be found on a BC exam. Now, interestingly enough, this first question is also completely approachable from the AB students. And that's sort of in line with the fact that the BC exam will be a significant portion of AB material. Like 70% of it or so will be the same material as you get on the AB exam. Maybe some free response questions will be slightly modified. The questions that they ask could be a little more intense, but a lot of it is the same. So we're starting off easy. We're beginning this series with the non-calculator section because it's just better to get a feel for the standards that we're going to be doing, the setup of these equations first, and then in the second half of the series we'll cover the calculator questions, which will use the techniques that we have already established ground rules for. We'll just be using the technology to help us with the calculations at the very end. Okay, so give yourself about, this one is 4 parts, so give yourself about, 12 minutes, maybe 10 to 12 minutes. Since you all are in BC, you should be able to do this fairly quickly. And then when you're done with your attempt, come back and see how we did it here. Maybe you'll learn something or two. All right, without further ado, let's get started. So we have this graph here. We have a function that's defined on this closed interval from -3 to 4. And we're given the initial condition. So the graph is actually f prime. So this is the graph of f prime. Got it. Consists of a line segment and just a semicircle. Nothing too intense. Let's look at part A. On what intervals, if any, is f increasing? So very easy to say that this happens when f prime is positive. You get points just for saying that. So in other words, we're going to look at when the graph is above 0. In other words, the y value of the graph. So that's simply going to go from -3 to -2. That's it for part A. Very, very simple and straightforward. We're going to interpret increasing to mean its derivative is positive, and then we're going to say, hey, the derivative is the graph that we're given, so we're just looking for when the graph given is positive. All right, great. Let's look at part B. Find the x-coordinate. Only the x-coordinate is needed here, guys, of each point of inflection of f. Okay, well, first we need to say that a point of inflection happens when f double prime changes sign. Okay, which means that f prime has a maximum or a minimum, has a relative max or a relative minimum. It doesn't really matter which one it has, just as long as the slope of the slope is changing sign. And since f prime is the graph that we're looking at, we're looking for when the graph has a relative max or min. Okay, so we can just use our eyes for that. It's pretty simple. Let's use our eyes. Here is a minimum. But you'll notice something interesting, that the second derivative doesn't exist here. You might wonder, does that matter? Of course we have a maximum here. Doesn't really matter. The slope is still going from negative to positive at that spot. So we're going to say at x equals 0, and at x equals 2. Okay. The idea here that can trick people of differentiability is that yes, the second derivative doesn't technically exist there, but that's okay because the first derivative does exist there, which means that the function is continuous. So the function is connected, it's just going downwards with a more intense slope, and then all of a sudden, it does something like this. Maybe I should draw it like this. Could totally go like that, right? Actually, I guess it would be a little bit different now that I think about it. It would be something more like this, and then I don't know, some kind of cusp where it still has a point of inflection there. That's my point. All right, let's look at part C. Part C is fairly straightforward. Find an equation for the line tangent. So you need to be able to do the equation of tangent line. Every time you see equation of tangent line, I want you writing this down. Y minus y value equals m times x minus x value. Or if they give you equation of the normal line as well. And they very graciously gave us the x value and the y value. So they're referring to that specific location. The specific location that they gave us as an initial condition, f of 0 equals 3. So we're going to have y minus 3 equals m times x minus 0. Well, what is the m value? That's going to be the slope at 0. So f prime at 0 is the value of the graph at 0, which is negative 2. So the equation of tangent line is simply going to be y minus 3 equals negative 2x. If you'd like, you can put y equals negative 2x plus 3. That's fine. That is the equation of tangent line at the point. Okay. And then for part D, we have to do some integration here because it says to find f of negative 3 and f of 4. Show the work that leads to your answer. Well, we have to use the Fundamental Theorem of Calculus here. The Fundamental Theorem of Calculus says that the integral from a to b of a derivative is equal to the overall change, the net change in the original, so f of b minus f of a. We're going to use this fact to say that the integral from 0 to negative 3, that's our first one, of f prime is equal to f of negative 3 minus f of 0. But what I would rather do first is I would say this is equal to the negative of the integral from negative 3 to 0. Which means this is the negative of f of 0 minus f of negative 3. Which would have been fine if we would have just called it, f of negative 3 minus f of 0. It's also valid, right? Totally valid. So then what can we say here? Well, we can say that f of 0 minus that integral equals f of negative 3. So let's just find out what this integral is equal to. We're going to have to use the graph to determine that. It's going to be determined by a line segment. So that's area from here to here. That area is going to be 1 by 1, so 1/2. And then this bigger triangle is going to be 2 by 2, so half of 4, which is 2. Remember that the area underneath the x-axis is considered a negative value for the integral. So overall, this is going to be 3 minus, let's see, that was 1/2 minus 2. So this is going to be 5 minus a half, or 4.5, or 9 halves if you want. That is equal to f of negative 3. All right, so this is all justified, showing the work, and we're using the fundamental theorem of calculus to kick it off. Let's do that with f of 4 as well. So we're going to say the integral from 0 to 4. We don't need to flip that because the limits are in the correct order. The integral from 0 to 4 is simply going to be f of 4 minus f of 0, which means now we're going to say f of 0 plus this integral is equal to f of 4. So let's find the integral from 0 to 4. That's using the graph again. This is going to be the area inside of here, which is some negative area. How much area is that? Well, if we take the whole sort of rectangle here, that's just 2 by 4, so that's 8. Minus the half circle, that's a radius of 2. So we have 1/2, because it's a semicircle, of pi r squared. So this turns into 8 minus 2 pi. That's how much is down here. Now remember, this is underneath the x-axis. So even though I made this region look like a clown's costume, with all the nose-looking things, this area, we need to consider it as a negative. We need to call it negative, basically, because it's underneath the x-axis. So this is going to be 3 plus a negative 8 minus 2 pi. So in other words, we could just call this 2 pi minus 5, and that is equal to f of 4. Okay, so we really have to be careful on these problems. When they're giving you a region, and we have to do some sort of side arithmetic, some kind of potentially distracting step that can make us forget that the area that we're calculating is underneath the x-axis, so this must be negative. First, we're treating it like it's just positive area. We're not even considering that it's on a coordinate system. We're just looking at the area in between this space, which would be something that you do like in a basic geometry exercise. But then we have to be smart and say, hey, wait, that's the area that we're interested in, but it's located underneath the x-axis. So technically, when we take the integral from 0 to 4, we're going to have to use a negative to represent that. Okay. Other than that, stuff is pretty straightforward. We're using the graph of the derivative to answer all of these questions. F is increasing when the derivative is positive. Point of inflection when the derivative has a maximum or minimum, which allows us to just look at the graph and see the features on the graph. Equation of tangent line, we just sprinkle that in there because you need to know how to do that for any kind of derivative calculus. And if you're in BC, it might have been a while since you've done an equation of tangent line problem. Learning Taylor polynomials and working with series and polar and parametrics, you sort of start to deviate from those basics in calculus. So it's good to come back, get a feel for them. Like I said, this is a BC practice exam question because there are lots of AB material questions on the BC exam, but you should be familiar with this stuff, so it shouldn't have taken that long. Anyways, that's enough blab out of me. We'll continue this AP Calc BC FRQ standards series with more non-calculator questions before we step into the second half, which is really the first half of the document that I'm using, but we'll get to the calculator questions some other time. I'll see you next time in the void.